Yes, good day, everyone. We are from group number S, and our presentation is about reverse engineering and redesign analysis of an industrial solenoid valve, focusing on the ASCO 8215 BO80, and it is also known as red hat gas air solenoid valve. This is a case study done for BK10A 3800, Principle of Industrial Manufacturing Process, prepared by Osama and me, MD Gholam Arif. In slide 3, first a quick context. Our target component is the ASCO Red Hat 8215 BO80, which is commonly used for gas and air control. Solenoid valves like these are critical actuators in many automation areas such as robotics, medical systems, fuel and pneumatical systems, power generation, because they convert electrical input into controlled mechanical flow. Now, the main issue we are addressing is that this is a more legacy style design, meaning it can rely on older material intensive manufacturing approaches. So our objective in this project is to modernize the valve design in the direction of Industry 4, mainly targeting improved sustainability and reduced cost. In slide 4, next I will explain our methodology, which started with structural disassembly plan. The goal was to reduce the risk of component damage and also preserve the assembly sequence, because that sequence matters for reverse engineering analysis. First step, external disassembly. We remove the valve cover or bonnet by losing the threatened fasteners. For that, we used a 3 by 8 inch combination wrench and a ratchet with extension. Second step, solenoid extraction. The solenoid assembly was removed using flat and star screwdrivers. And for gripping and pulling where needed, we use a grip plier. In slide 5, after accessing internal parts, we handle the internal core and flanger component carefully, because these are precision surface, scratches or dents could create sealing issues or friction problems and ruin the analysis. And in slide 6, after cleaning and visual checks, we move to dimensional analysis. We measured key dimensions using digital vernier calipers. The critical measurements include armature diameter and valve seat or orifice diameter. These measurements support our component assessment, and they become inputs for redesign decisions. And in slide 7, finally in the methodology, we perform basic material identification using simple non-destructive tests. We used magnetic susceptibility testing to identify which components are ferrous, and density weight estimation and tractic assessment to distinguish non-ferrous metals and polymer parts. And importantly, we did data recording and cross-checking also. Photos, measurements, material results were documented and organized by component. Then we compared what we found with standard expectation for solenoid valves. Now, my mate Osama will go through the rest of the slides of our project.
Thank you very much. So moving on to the results of our teardown. On the right here, you can see the complete exploded view of our valve. And we also structured the bill of materials by breaking the main systems down into their individual manufacturing components. So first we have the pressure vessel, which includes the die-cast valve and bonnet, items like 1 and 2. And second, we have the diaphragm assembly, item 3, which seals the main flow. And finally, we have the solenoid actuator. So instead of listing this as one big unit, we broke it down into items 4, 5, and 6. So the base assembly, the coil, and the flux washer. And by separating these, we could identify the distinct manufacturing processes for each part, such as like a deep drawing used for the base and the winding used for the coil. So upon closer inspection, we identified like 3 critical inefficiencies for our legacy design, or old one. So as you can see on the left photo, the armature surface shows like concentric feed lines, and this process was made by CNC turning. And machining a cylinder from the bar stock like this, it weighs approximately like 45% of the raw stainless steel. Efficiency number 2, looking at the valve body on the right, the internal flow path has a sharp 90-degree turns. So the fluid dynamic principles tells us that this causes turbulence and pressure loss. Inefficiency number 3, the solenoid, it uses a solid iron core, which generates heat due to eddy currents. And our first and most impactful redesign addresses the armature. So we propose switching from CNC machining to multi-stage cold forging. And as the diagram shows on the right, forging retains the material grain flow, improving fatigue strength. And more importantly, we look at the math. On the left, we calculated that the current machining process costs about $1.05 per unit, and by switching to forging, we estimated that it will cost approximately $0.55 per unit, and which is approximately 45% reduction in manufacturing costs. And for the remaining inefficiencies, we proposed 2 further changes. First, for the flow, we could use CFD topology optimization to smooth out the sharp corners and in the casting mold. And this will reduce the turbulences and improve the flow rate. And second, for the magnetic circuit, we propose replacing it by composite iron core. So instead of solid core, we would use composite iron core, and this will reduce eddy current losses. We also suggest adding a magnetic latching feature, and it will allow the valve to stay open without consuming any electricity, which is massive energy saver for the long-term operation. And to validate our redesigns, we created this table, which has the weighted decision matrix comparing the original design to our proposal. And we weighted the manufacturing costs and sustainability as the most important factors. And as you can see in the table, the original design scores 37 out of 100, and our redesign scores 92.5 out of 100. And this massive improvement is driven by the 47% reduction in costs and the elimination of steel waste via the forging process. And this proves the redesign is actually economically viable. In conclusion, for the sustainability, we moved from wasteful machining to net sharp forging, and we optimized the flow path to reduce resistance, and we also utilized composite materials to achieve faster response times. And this project, we successfully demonstrated how a legacy industrial component can be modernized for the Industry 4.0 era. And our proposals are also supported by research from 2022, 2025, especially regarding multi-physics simulation and cold forging processes. You can check them out, interesting research articles, and that's all. Thank you very much for your attention.